Good afternoon, everyone. My name is Priscilla. I don't know if you all can see my slides on the screen. I'm the next presenter for today. Can everyone see my slides, please?
Yes, please, go ahead.
All right, thank you.
Yes, we can see it.
Thank you. Like I said, my name is Priscilla Ogunlude, and I'm a researcher at Robert Gordon University. This presentation is about mass transfer characteristics through alumina membrane to different pore sizes and porosities. And I'll just start by taking you through the research overview, the methodology, the results and discussion, as well as the conclusion. Basically, we're producing biogas, first of all, and trying to get it separated to a higher value fuel. So basically, organic waste is fed into a digester, and that's the natural process that occurs to produce biogas. Once it goes under some processes under certain temperature and pressure conditions, biogas is formed, and and it can be used for a variety of purposes. So for electricity generation, used as fuel for cars and also cooking and heating at home. CO2 be used for photosynthesis, can be used, basically the ecosystem relies on this sort of processes. Biogas can be separated through four major methods. The first of which is absorption, which relies on the principle of preferential solubility. So this can be either water absorption or chemical absorption with chemicals such as polyethylene glycol. Another method is pressure swing adsorption, where the system acts like a sieve. It swings into high pressure and then it absorbs gases and then swings down to low pressure and then dissolves the gases that are wanted. Cryogenic distillation also works at high pressure, but uses low temperature. It's a very expensive process. I'll be focusing on membrane purification, and this is what my laboratory setup looks like. So basically, the biogas mixture or biogas components are in the cylinder and is passed through a pressure gauge and the membrane module. Comes off as the retentate, and then the unwanted gas as permeate and retentate gases goes through another flow meter and gives us some of the information that we use to analyze the behavior of the gases. This is also sort of a schematic showing what happens and with regards to pressure, flux, and basically the permeation of gases, in this case, majorly methane and CO2. The major things that we're considering in this work were the effect of pore size, porosity, and tortuosity on the permeance of gases, against CO2 and CH4, which are the major biogas components. And we found that the permeance decreases with an increase in pore size. And this can be clearly seen from the graph. The graph also shows us that from the equation that there's a mixture of Norton diffusion and viscous flow with the behavior of these gases. We also found that as porosity increases, the permeance decreases. So, and we're able to get the relationship between porosity, tortuosity, and pore size. We found that pore size and tortuosity are directly proportional, and that and that there's a parallel transport mechanism, like I said, which is a mixture of viscous and nozzle flow, and that the effect of pore size on fluid behavior is very important, as well as the porosity. From our findings, we're able to go further to further reduce the pore size so that we can increase the permeance and also the selectivity of the membranes, by coating it as well, so that we have some a preferential solubility. So it's going to be sort of a mixture of absorption and membrane separation, which is one of the advantages of this technique. We're able to use, we're able to put, a coating and also harness the advantages of other separation types. So this technology is found to be viable and can be adapted to biogas upgrading to a high heating value for and contribute to worldwide emission reduction target. Thank you for listening. I'm happy to answer any questions.